Okay. Um, there are several functions that we need to know, and we need to know them quickly in terms of our ability to graph them, know some stuff about it, domains and ranges and that kind of stuff. So the first one we're going to look at is the constant function. And the constant function is just a flat or a horizontal straight line. For example, this one could be f of x is equal to 2. The domain would be all real numbers, because you can have any x and there'll be a y value. The range is the value that we have, so in this case it would be 2. It has symmetry. Across the y-axis it can flip, so it has y-axis symmetry. And that would make it an even function. And the unique features, I guess you can just say it's a horizontal line. Another straight line that we gave a specific name is the identity function, and that would be f of x equals x or y equals x. Again, since it's a straight line, all real numbers for the domain, it does go up left from left to right, so the range is also all real numbers. And then this one has origin symmetry, and you can see that here from 1, 1 and -1, -1. So you can see from the picture that it has origin symmetry, and that makes it an odd function. And in terms of unique features, I mean, it is a straight line, so it has a slope of 1 in this case, so that might be a unique feature, that the slope is 1. But nothing particularly difficult about those two. Then the quadratic, and this is just the straightforward y equals x squared. Again, you can square any number. The range here is starting at 0 going up to infinity, and you can change that. You can mess with that a little bit. For example, this would clearly still be a quadratic, but that one would go down. But y equals x squared goes through 0, 0 and then up on both sides. Symmetry, it's even, so it has y-axis symmetry. It's actually the graph that I have in my mind if you ask me about even and odd functions. And the unique features, well, I guess it has the shape has a special name, and it's called a parabola. Other than that, it has a vertex, and the vertex is important for graphing any parabola. So a cube function is pictured over here. So it's similar to x squared, but clearly a little bit different. So all real numbers again, and part of that is because both x squared and x cubed are polynomial functions, and we'll get to that later in the year, but that's all polynomial functions have a domain of all real numbers. The range, well, because it's a cube, it can be negative, so this range is also all real numbers. I guess I forgot to write that, so if I want to write that like an interval, you could do it this way. Symmetry, origin, and just like even and x squared, origin for me goes with an, x cubed goes with the odd functions. That's the one that I have in my mind to make sure that I'm doing things right. And unique features, I guess it goes to the origin. It goes to 0, 0. And other than that, not sure that there is a lot of other stuff that you need to know about it. Square root functions. Like square root to me is like only half of the function, because the square root is related somehow to this one, right? So squaring it and then taking the square root, so they're inverse. But you have to cheat this function a little bit to actually end up with an inverse. So, but this is what it looks like. The domain would be that whatever's underneath the square root, well in this case it's the square root of x, so whatever is underneath the square root needs to be larger than or equal to 0. And we've seen that a couple times already this year. So if you had a square root function like this, 2x minus 1, then it would be 2x minus 1 needs to be greater than or equal to 0. Okay, so again, the argument needs to be larger than or equal to 0. The range, so I call this a starting point. So this one starts at 0 and goes up. And in terms of the starting point, it actually is both important to and the domain and the range. But this one goes from 0 to infinity. It does not have symmetry, because it doesn't reflect across the y-axis or through the origin. and the unique features. So for me, I call this half a graph. And that, again, has a little bit to do with the fact that it's supposed to be inverse to x squared. Okay, then the reciprocal function, or the inverse function, that's the 1 over x. It's called also part of our hyperbolics. It's the most straightforward hyperbolic we have. The domain is all real numbers with one small limit, and that would be that you cannot divide by 0. So when it says 1 over x, well then x cannot equal 0. If it was a function that's slightly more difficult, like 1 over x minus 1, then x minus 1 wouldn't be able to be equal to 0, and you could then say, for that one it would be this. X can equal 1. Range, well, I get every value I want except 0. So you can see that on these pictures here. And so it does have a slightly limited range. So trying to figure out, this is probably a good way to write it. So it goes from negative infinity to 0. Oh, can I have a square bracket? Because it's not actually, it does not go through 0. And from 0 to infinity. So that's one way to write it. You could do it with intervals as well. I guess you could even do this, all real numbers except y cannot equal 0. Origin symmetry. And then the unique features, I definitely need to mention here that it has asymptotes. So on this picture, this is an asymptote. The x-axis is an asymptote. The graph will approach it, but it will never cross the x-axis. And the same thing with the y-axis. The graph is going to approach it, but it's actually never going to cross. So asymptotes are important for hyperbolics. We have two left. We don't do a lot with these per se, but they do occur quite a lot, and you definitely need to be familiar with them. So an absolute value function, the domain is all real numbers. You can put whatever you want in there. And this particular one goes through 0, 0, and then since it's an absolute value, it's always positive, so from 0 to infinity. Symmetry, yes, across the y-axis, so it's even. And unique features, and we don't really call this a vertex, because that goes with parabolas, so I don't think that I really want to list any unique features. I guess I could just say it has a V-shape, because they do have V-shapes. Inverted, you could still call it a V-shape. So, and then the last function we have is the greatest integer function. So the greatest integer function is sort of a weird one, but it happens a lot in word problems. And so what it does is it looks at the number. For example, if I look at the number a half, then it finds the greatest integer that is near it in terms of equal to or less than. So the nearest integer that's equal to or less than a half would be 0. So when you're at a half, you go to 0. I think this one is on there, or this one. So 3 over 4 is also on the table, for example, and you would still be at 0. So not until you get to 1 at f1, now you get to round it, or not round it. Now the function takes on a value of 1. And then sort of the process repeats. So at 1.5, it would still be 1, etc., etc. So it's, I'm not sure why they call it the greatest integer. I think it's a bit of a misnomer. It's actually the smallest integer that we're near to. The domain, all real numbers. The range, all real numbers that are integers. So it's the set of integers. So we'll call the range just the integers. Does not have symmetry, unique features. This is a very common name for it. It's called a step function. So it has steps. Okay, and then part of that is that the bottom one's filled in. So you see the lower dot, or the solid dot, is always on the left of these little lines, and it's open here. And again, that has to do with, like, if we look at 2, for example, if I'm at f 2.7, I'm still at 2. If you are at f 2.9999999, you're still rounding to 2. So, and then as soon as you're worth 3, then the function takes on a 3. So I hope this makes sense. Thank you.